Hello, free thinkers. Before we get started, go ahead, hit that like button, subscribe, and leave your comments below. We're going to talk about LaPoint arrays and what I am building. So if you will take a look here, this is a modified LaPoint array. These are the big ones. They've got 6 levels. These two attract quite strongly, I might add. When they come together, boy, you got to watch. This thing will really pinch your hand badly. Now, some really cool things about these are when you take small magnets and you push them through in the way they don't want to go, it will throw them. Which, is cool. And you can see they're magnets. A weird thing that I didn't know when I started making these is that if you look close, they have a hole in the center. That hole, anytime you have magnetism in all the other places, like when I'm building them, you can see I've got a few spots in my little one where I don't have it. Anywhere there is no magnet, like right here, whether it's attractive or repulsive, if there's magnetism all around and no magnetism in one spot, the magnets will avoid it as if it's an opposite pole, but it's not an opposite pole. It's just a lack of magnetism. And I think that's really interesting because it goes into my theories I write about how magnetism will always go to the strongest point of magnetism. So, for example, this is Robert Murray Smith uploaded this right before he died, and I was all over it. I downloaded it immediately. And what this is it's called a V-gate. And this V-gate is very special because, see, what happens is it's meant to spin like this, obviously. And I've put a magnetic gradient into this one. So there's 2 gradients. One gradient is the one you get in shape. So obviously at the tightest part of the pinch, magnetism is the strongest. And as it goes out and it separates, the magnetism gets weaker and weaker. Okay, so that's one gradient where it's strong here, it's weak here, and in between here and here, it goes smoothly weaker, 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 weaker around. Now, most of the time when you have these, they spin. So what you do is you take another couple magnets and you push them down right here. And if they attract, it'll follow the magnetism to the most attraction. So you push them down and it will wrap around like this. But normally what happens is when they get back to the center, they get stuck. So what I've done is I've used N40 magnets here at the small pinch and then N52 out here at the big pinch. So theoretically, when you push the magnets down, it wraps around. And then when you get to this spot, see how the magnets are pretty much equal? The magnets have to make a choice. Where am I going to go next? And if you don't have any difference in the strength of the magnets, then you won't get continuous spin. But if they're faced with a choice of, I can pick N52 here or N40 here, it will pick N52. And then when it makes that jump, this gradient, the shape gradient, will take over. So there's a shape gradient that moves it around, and then there's a strength gradient between the physical magnets here that pulls it past the lump. Okay, now, if you further combine that with the pinch pull effect I showed in my earlier videos, where if you pinch like this, if you pinch them this way, you can get round magnets to roll back and forth. If you pinch like this, the magnet moves back and forth like this. And obviously, if we were to have the V-gate out here, and then we use these magnets, which again, There's another shape gradient because down here at the bottom, they're very tight together. But then up here at the top, they're very far apart. That's another shape gradient, just like the V, except this one's 3D and hemispherical, okay? So if we use that shape gradient together with the V gate, I think that we can get continuous spin. And if we can get continuous spin, we can get continuous power basically for free. So my tiny arrays are getting pretty close to done. You can see I've only got a few more spots there to fill in. And I'm pretty surprised that these are 1/8" magnets and my printer was able to print them pretty much no problem. So what's going to happen with these is you'll be able to take them and push them down together like this. And they'll float in there, which it doesn't float right now because I'm not done with it. But you see what I'm going for. And then ultimately, we can get 3 of them and put them all together like this. And then what will happen is, because you have 3 together, when you shove them, a steel ball or a magnet in through this hole, and then they're all crushed together like this, you'll get a very strong reaction. So not only can we throw magnets, but we could also do some more exotic things too. But first I got to get all these arrays built. So that's it for today. I'm going to keep working on my magnet arrays, and you guys let me know what you think down in the comments. And as always, be a free thinker.